Okay, I want to go through this, the solutions to the test. First question, given that a sequence converges to A, we want to prove the absolute value of the sequence converges to the absolute value of A. So of course we begin with let epsilon be greater than 0. And we're going to need to define K. We're going to let n be greater than K, and we want to prove that absolute xn minus absolute A is an absolute value of the difference less than epsilon. So you can see pretty clearly that this sequence tells you how to relate that difference to absolute value of xn minus A. One is just less than or equal to the other. And that's something that we can control using the fact that xn converges to x. So, let's define. Gotta apologize, I still don't have a working pen, so this is all coming out kind of crude, I apologize. We're gonna be defining K so that if little n is greater than capital K, then absolute xn minus A is less than epsilon. Let n be greater than capital K. That means that absolute xn minus A is less than epsilon, which in turn means that the difference in absolute values is less than or equal to the difference in quantities, which is less than epsilon, and we're done. Okay, that's all that proof required, was using, this is really a choose statement here, I said define, but using the choose statement to make xn minus A less than epsilon, and then immediately it follows that the difference of the absolute values is also less than epsilon. I meant that to be a kind of easy but deep warm-up. Okay, so here we know that for all n, xn is less than n1. That's what we mean by a bound. And for all n, yn is less than n2. And we're going to prove, what do we think is the bound? N1 plus N2. And you'll see why we think that in a moment. How do you prove that? You choose N. Let N be in the natural numbers. We know that Xn is less than N1. We know that Yn is less than N2. So if we add them, Xn plus Yn is less than N1 plus N2. And these should really be less than or equal to's. That's it, okay? That was an extremely straightforward use of our proof techniques. It did require recognizing that these two inequalities suggested this one. Okay, now B was a mistake. I had originally intended to do bounds on both sides, thought about using the Bolzano-Weierstrass, and then switched to bounds on one side. So this isn't quite true. What I was looking for you to say is, since xn plus yn, that some sequence is bounded by Bolzano-Weierstrass, it contains a convergent subsequence. That's all you need to do. Now, unfortunately, it's only bounded above. If you try, you will easily come up with an example of a sequence that is bounded above, but does not contain a convergent subsequence, because it's not bounded below. So this was a mistake. Most people got this just fine. I am sorry for that mistake. And of course, this wasn't quite correct, but it was what I was looking for, so of course I gave it full credit. Okay, people really struggled with this one, and I think if you did, there's an important point that you should get straight. The set, yeah, I think I'm gonna start by writing out the argument in the case of A, and then drill down about what people weren't getting about the set. So this set, I'm going to say it out loud, is the set of all numbers x in R whose square is less than 5. So if your square is less than 5, you're in this set, and if your square is not less than 5, you're not. That's the set. And anything you write down about the set has got to flow from that. So if you want to prove that 10 is an upper bound for S, you want to prove that for all x in S, x is less than or equal to 10. So you start, as most people recognized, with let x be in S. The first thing you should do is say what that means. So x squared is less than 5. And we want to end up with x is less than 10. Okay, 2 ways you can go here. One is you can recognize that if x squared is less than 5, that tells you that x is less than the square root of 5 and greater than minus square root of 5. Those are 2 things it tells you. And since square root of 5 is, of course, less than 10, x is less than 10. That's how most people did it. Perfectly good argument. Along the way, you recognize that a more simple description of S is the set of points between minus root 5 and plus root 5. A more, this requires knowing something about the square root of 5 that maybe we didn't prove, but a more, a less involved way, I mean, I guess more conceptually involved, but you could just say, well, if x were greater than 10, we only need less than or equal to for the bound, I believe. If x is greater than 10, then x squared is greater than 100, which is greater than 5. So, contradiction, x is less than or equal to 10. I like that better because it just takes the definition of S and works straight from it. But either way is fine. The point is, if you're thinking about what the set is, you recognize that the least upper bound is the square root of 5. That's all I was looking for in B. And then in C, I asked you to prove it. Remember, there's 2 things to prove. 1, square root of 5 is an upper bound. And again, the best way to write this is let x be an S, so x squared is less than 5. That's all you know about x. And then from here, you should argue x is less than the square root of 5, which is, of course, a one-line argument. I wish I'd been clearer about this from the beginning. There's several equivalent ways to write the second condition, and I offered them all, and they're all equivalent, and I went between them. And I wish I had been more precise on this. I think usually the easiest way to prove that something is the least upper bound is to say, if B is less than the claimed upper bound, there exists an x in S which is bigger than B. What does that mean? That means that B is not an upper bound. Okay, so everything square root of 5 is an upper bound. Everything less than square root of 5 is not an upper bound. I really emphasize, I think that once you're proving square root of 5 is the upper bound, you should stop. You should call it square root of 5 or whatever you think it is. Or if it's a number, stick with that number. People who kept calling the square root of 5 B and kept writing B equals the square root of 5 several different times, and then would start doing things in formulas where they were proving that B was equal to the square root of 5 or proving that it wasn't equal, and just got themselves muddled by holding on to 2 quantities that were equal, B and square root of 5. In any case, so this is it'd be better to call this B prime, because that's what the book calls it. So if B prime is less than square root of 5, we need to construct, so let b prime be less than square root of 5, we need to construct something in the set S which is bigger than the square root of 5. The standard trick is to take the average, b prime plus square root of 5 over 2. The reason for that is we've seen many times before that b prime plus square root of 5 over 2 is between b prime and the square root of 5. So that means it is bigger than b prime. That's what we wanted. So we get one of these right away. And it's less than square root of 5, which does not mean that it's in S, right? Less than square root of 5, there are lots of numbers that are less than square root of 5 whose square is not less than 5, negative 10, for example. So we need something else to guarantee that X is an S. We've seen this before. So we need to take, let's say, 0, because minus square root of 5 is less than 0 is less than square root of 5, which means that the max X, if both of these numbers are less than the square root of 5, the max S is also less than the square root of 5. And if one of these numbers is greater than the square root of 5, then X, which is the maximum of the two, is greater than the negative square root of 5. So X is in S, and X is greater than b prime. That's the proof. And lots of people were confused about what S was. Lots of people got lost in the logic of constructing an element of S bigger than b prime, and lots of people lost the subtlety that to be an S, it needed to satisfy two conditions. Okay, 4 was one of the 17-point problems. I think it was the easiest. I will apologize for one thing that maybe made it harder. In here, I left an extra m that had nothing to do with the problem. And that may have thrown some people. Okay, so I'm going to set it up before I do any deep thinking. Let epsilon be greater than 0. We're going to have to we need this to be true. So we know, I'm going to write it like this, choose K1, so that if n is greater than K1, then absolute xn minus x is less than epsilon 1. And sometimes there's been something more complicated connecting K1 to K, but let's just start with trying n greater than K1. Basically, treat K as K1. That would mean that xn minus x is less than epsilon 1. So here's our task, right? You can see we can guarantee by making it go past K that xn is within epsilon 1 of x. We need to guarantee that axn is within epsilon of ax. It is, I think, pretty clear what you should do with this equation to make it look more like this equation, which is to multiply it by a. Right? A times xn minus x is less than a epsilon 1. On the other hand, since a is positive, that's equal to axn minus ax. Okay? So the whole argument goes through as long as a epsilon 1 equals epsilon, and that's easy to accomplish, right? We just have to make epsilon 1 be epsilon over a. We know that's greater than 0 since a is positive. Nice to check that. at the same time, we can stop being coy. K is really K1. Epsilon 1 is epsilon over A. And that's the whole argument, okay? All you do is choose K so that xn minus x is less than epsilon over A, and axn minus ax is less than epsilon. Prove the sequence is Cauchy. We're going to let epsilon be greater than 0. We're going to define K. We're going to let n be greater than K. And then we need xn minus xm to be less than epsilon. Of course, you should be doing this on scratch paper. And I apologize, I'm too lazy. Each of these terms is going to 0 very rapidly, so it makes sense to use the triangle inequality and say that the difference, they're both positive, so the difference is smaller than either one alone. So you can write that as 2 to the minus n plus 2 to the minus m is less than epsilon, or than the sum of each alone. So it suffices to make 2 to the minus n less than epsilon and 2 to the minus m less than epsilon. How do we do that? Okay, now I will do scratch paper. Easiest thing is the log of both sides. Log 2 to the minus n less than, oh, these are over 2, sorry. We want to do our standard trick of making them each less than epsilon over 2. Log epsilon over 2. And that's minus n log 2 less than log epsilon over 2. So we end up with n is bigger than minus, switching some signs, log of epsilon over 2 over the log of 2. If you use log base 2, you can save yourself some work. So k is minus log base 2 epsilon over 2. And then it follows immediately, right, where this should be n and m. N is greater than minus log base 2 epsilon over 2. M is greater than minus log base 2 epsilon over 2. And then we just unravel that. 2 to the minus n less than epsilon over 2. 2 to the minus m less than epsilon over 2. Another option is to notice that 2 to the minus n for every natural number n happens to be less than 1 over n. You want to check carefully. Some people did this and didn't quite get it right, so that it didn't work for all n. But when n is 1, it's smaller. When n is 2, it's smaller. Once you get 3 and higher, it's clearly getting small faster. So that works well, and then you can take k equals 1 over epsilon. Either is a good approach. Last problem. We are trying to prove, what we're given is this special fact about xn minus xm, and we want to prove that it's Cauchy. So let epsilon be greater than 0. Define k equals, let n m be greater than k. We want to end up with xn minus xm is less than epsilon. But we know that xn minus xm is less than 1 over min and m. So it would suffice if we could show that 1 over min and m is less than epsilon, which is the same as showing that the minimum of n and m is greater than 1 over epsilon. So we just need n and m to both be bigger than 1 over epsilon. So we make k equal to 1 over epsilon. And so n is greater than 1 over epsilon, m is greater than 1 over epsilon. So the minimum is, and we're done. Okay? Really was a quite simple argument. You had to wrap your brain around how to use this condition, and clearly this condition is putting 1 over min nm in the role of epsilon. So that's that's essentially how we went about it. We took that to be a stand-in for epsilon. In this argument, we saw we needed it to be smaller, and then we, as all usual, solved for m and n. Okay, couple of general thoughts about this. You could see several times the choose so that, using typically the definition of a sequence to give you a k with some property, and then using that k and getting to choose the epsilon 1 allowed you to make a powerful argument go through. That's an important thing. Following the epsilon, k, and so on structure that are the structure about proving from definitions with the quantifiers, really important. Having a sense about, in any given problem, you should think of epsilon as very small, you should think of n and m and k as very large, you should think of xn as not necessarily having anything to do with n unless there's a formula connecting them. If n is bigger than something, xn is not bigger than that same thing. You keep in mind the tricks that we have, and try to form an intuition about what that set that you're talking about is before you start arguing with it. I know that's really hard to do in a 50-minute test with many, many questions. Not the ideal way to do a test. Many of you are beginning to wrap your brain around it. If this did not go well, but you feel like you are wrapping your brain around this stuff, you're still doing fine. Do not worry. Keep doing what you're doing. Keep working with me. Okay, that's all I have to say, and if I can manage it,